Have you ever looked at a really complex problem and just wondered how engineers manage to find a simple, clean answer? Well, today, we're going to tackle one of those classic engineering puzzles. It looks like total chaos, I promise. But by the end of this, you're going to see how a really powerful method can find some beautiful order in all that mess.
So, take a look at this bolt. It's getting pulled in 4 different directions, and each pull has a totally different amount of force. It's a chaotic 4-way tug of war. The big question is, who wins? I mean, which way is this bolt actually going to move, and exactly how hard is it getting pulled?
So yeah, that's our challenge. With all these forces yanking it at all sorts of different angles, how could we possibly figure out what's going to happen in the end?
It definitely looks messy, I'll give you that. But what if I told you there's a powerful and actually pretty elegant method to just cut right through all this confusion and find one single clear answer?
That method, that's our secret weapon for today. We'll call it the XY game plan. This is the exact strategy engineers use to solve problems like this all the time. It's really all about breaking things down into much simpler pieces.
And the core idea behind it is something called vector components. All that means is that any diagonal force, like that 150 Newton pull, can be thought of as 2 separate forces working together. One that's pulling purely sideways on the x-axis, and another one that's pulling purely up or down on the y-axis.
And that leads us to our beautifully simple 3-step plan. First, we're going to break down each of our 4 forces into their horizontal and vertical parts. Second, we'll add up all the horizontal bits to get one total, and then do the same thing for all the vertical bits. And finally, we'll just recombine those 2 totals to find our single final answer. Simple as that, right? All right, it's time to put our plan into action. Let's do this. We're going to go through each of those 4 forces from our diagram and get step 1 done, the methodical breakdown into x and y components. And here's the breakdown. Okay, so force 1 at 30 degrees, it's pulling both right and up. Makes sense. Force 2 is mostly pulling up, but also a little bit to the left, and that's exactly why its x component is negative. Force 3 is the easy one. It's pulling straight down, so its x component is just 0. And force 4, that one pulls mostly to the right, but also dips slightly down, which gives it that negative y component. See how that works? So we've done it. We've broken every single force down into what we can call Team X, all the horizontal players, and Team Y, all the vertical players. The next logical step, of course, is to add them all up and see which team is stronger overall. Let's start with Team X. When we add up all those horizontal components from the table, boom, we get a powerful combined force of 199.2 newtons pulling to the right. Okay, now for Team Y. We add up all the vertical numbers, and what do we get? The final result is a much smaller but still super important force of 14.3 newtons pulling upwards. We've really done the hard part. We took 4 totally chaotic forces and boiled them down to just 2. So now we're at the final step, the grand finale, where we combine these 2 to reveal the big prize, the single resultant force. Just think about what we've actually accomplished here. That really messy diagram we started with has been simplified into just 1 horizontal force and 1 vertical force. And mathematically, what we've created is a simple, easy-to-solve right-angle triangle. And this visual just makes it all crystal clear. This is our final move. We have our total x force of 199.2 newtons and our total y force of 14.3 newtons. The final overall force, which we call r for resultant, is simply the hypotenuse of this triangle. All we need is a little Pythagorean theorem, and we've got our answer. And there it is. After all that pulling and tugging in every direction, the net effect on that little bolt is a single force of 199.7 newtons, pulling at a slight upward angle of just 4.1 degrees. That's it. That's our winner. Now, okay, solving a textbook problem is great and all, but why does any of this actually matter? Well, this isn't just some abstract puzzle. This exact principle is literally the foundation of how we build the world around us. For a bridge, engineers use this to make sure the combined forces of, say, wind and traffic don't create a resultant force that pushes the whole structure past its limits. In aerospace, they're calculating the resultant of thrust, lift, drag, and gravity to control a rocket's flight path. It's even in robotics, figuring out the precise force a multi-jointed arm needs to apply to lift an object. It's everywhere. So, the next time you walk across a bridge or just look up at a skyscraper, take a moment. The entire structure is just a massive, incredibly complex version of our simple little bolt, with countless forces all in perfect balance. It really leaves you with the final thought, doesn't it? What invisible forces are holding your world together right now?